Okay, so welcome everybody to the sixth and last session of our PhD course on mirror symmetry and Landau-Ginzburg models given by Professor Cruz Morales from National University of Colombia. Thank you very much, everybody, especially to Alex.
Thanks, Marina, and thanks everybody for coming, to be here in the last section. So we, 3 weeks and you are still here, so that's very good. So today I want to discuss this, set of ideas about mirror symmetry for heat-sink system. It is kind of very speculative picture. Is some ideas I have been working and I have been thinking of how to use this Aganagish picture I described last session to the heatsink system. So today, I just want to share with you these ideas, and some of the ideas could be wrong, some of the ideas could work. I don't know, but you know, I guess that you will find something interesting to consider, and maybe we can discuss later how to uh, work out this program. So let me just start with some motivation. So for this thing. So okay. So okay. So I'm gonna start with some motivation. So for this. So there is this work by Gamache, Green, and Webster about somehow they study mirror symmetry. They study mirror symmetry for multiplicative. I will say what this multiplicative means in a second. Hypertoric varieties. Okay. So roughly speaking, a hypertoric variety. So roughly speaking, is just an hypercolor adult of a toric variety. So this is a hypercolor hypercolor analog of a toric variety. And there are these two types of this hypertoric variety, the so-called additive hypertoric. So this additive hypertoric variety are, somehow the column branches of n equal of three-dimensional n equal 4 theories we discussed last time. So these are somehow the column branches of three-dimensional n equal 4 gauge theories, right? So this is somehow what in the notation of the last session was the x, in the Ganagish one. Okay. So how these column branches, I mean, the mathematical definition of column branch is not that simple. There is some work by Braverman, Finkelberg, and Nakajima. So they try to describe mathematically the column branches and assuming uh, some cotangent conditions. So they somehow describe this column branches for certain theories. But it is kind of very interesting problem in mathematics to really give a mathematical description of these of these objects, right? But they are essentially the additive hypertoric varieties. So this column branch is a source of this uh, additive varieties. On the other hand, we have the multiplicative hypertoric varieties, right? Somehow the source of these hypertoric varieties are certain integrable systems. So there's cyber, Witten systems, somehow governing a four-dimensional n equal to 30 theories. So in the previous lecture, language will be this curly Y or Y check in the English. Yeah. So we have these two things, and there is some relation between this multiplicative and this additive hypertoric varieties. This is a conjecture by Gamache, McBreen, and Webster. So Gamache, McBreen, and Webster conjecture is a relationship between this additive and multiplicative hypertoric variety. So let's consider, let U be a multiplicative hypertoric variety. Okay. Then that exists an additive hypertoric variety is called M, some divisor in M, a divisor D in M, and some isomorphism U is equal to M minus D. So that's how to say that somehow you can see that the difference between this a multiplicative hypertoric variety and certain additive hypertoric variety will be some divisors. If you remember last time when we discussed the how to construct the mirror of the column branch X, and we consider this Y check, so we see this some instance of this conjecture, because remember last time. So last time we used the fact that the Y check will be this X minus some divisor D check, right? So in that sense, this Y check was actually the multiplicative hypertoric variety, right? And this X was the additive. And the way we used to construct this the mirror of X was actually using some instance of this conjecture, so that when I say that this conjecture said that we can put this in a more general setting, right? That's interesting. And then we can actually use this to construct the mirror of this additive variety. And in fact, we can do it in general. There is this theorem by Lau and Chen. So the theorem said, okay, so consider an additive variety, let M be an additive hypertonic variety. So then is M is so they put it this HYZ mirror. So remember that the first lecture we see that there is this picture of mirror symmetry using the SYZ conjecture, which is using this kind of dual Dora vibration. So that's what they meant here. So adapted to this setting. So to the Landau-Ginzburg model. So the mirror is a Landau-Ginzburg model. Landau-Ginzburg. Landau-Ginzburg model. So you check W. You check. See, you know, whose underlying space you check is a multiplicative hypertonic variable. So in particular, the complement in M, the additive variety of a divisor D, or divisor D, is SYZ mirror to the multiplicative. To the multiplicative hypertonic variety. You check. Okay. And this was actually what we did last time when we construct the mirror, because we actually use this conjecture, right? So we see this relationship between y check and x and the check. So actually we use somehow the mirror of y, which should be this the mirror of this y check, which should be y, that we should be also it's also hypertonic variety, because essentially it's because remember that the relationship between y check and y was just hypercurrent rotation, right? So in certain sense, it's kind of self-mirror, right? So we get this thing, and then we construct the Landau-Ginzburg model, adding in the divisors in order to uh, to get the potential, right? So that's somehow the content of this term. So this Landau-Ginzburg model here, so was the one actually we constructed with the Y last time, right? And we discussed the Aganagish picture, right? And then, as we said, okay, so actually the relationship between this M and this Y should be some kind of, the difference will be with some divisors, right? But yeah, you somehow in the Aganagish, we have this Y and Y check, in the sense that you need to kind how you take this hypercolor structure, right? One of the other are use the notation of the structure, right? But somehow the Aganagish mirror, actually the two-dimensional mirror, enter in this picture. But this is, you see, this is just the upstairs mirror. So this the Lau theorem. I mean, if we use the Gamache-McBreen-Webster conjecture plus this Lausen theorem, so what we get is just the upstairs mirror. You see, there is no torus action here, so there is no core, there is no mirror of the core, which is also Landau-Ginzburg. There is no downstairs part, but it seems that we can somehow do it. So the first proposal is, the first thing I want to propose is, as a project to work. So the first project I want to propose you is, okay, so how about we use this equivariant mirror in a gonna sense and put these ideas into this context. So the first proposal will be that the Aganagish equivariant mirror. Symmetry can be formulated, sorry, can be formulated, or should be formulated by the, should be formulated in this context. Okay, so we probably should to use some torus that actually scales the holomorphic symplectic form of the additive variety, define the core, right? Get the mirror of the core and see that, actually this multiplicative variety here, you check actually fibers over this U, which is actually the mirror of the core, and then we can construct the potentials and see that adding this action. So we have to add some twisted masses in the upstairs potential, and also this correspond to some twisted masses in the downstairs potential, which actually are the mirror of the equivariant parameters of the torus action. So I think that this should be possible to be implemented in this picture, right? That's the first thing, right? But there is another question. So you see that this here. Let me just go back here. So here, actually, we have this, source of examples of the multiplicative hypertoric varieties as certain integrable systems related with some 4D theories, n equal to theories. So we're gonna ask, okay, where actually you see other kind of systems arising in this context, right? So that probably there should be another kind of integrable system or some integral system related to these theories, some kind of analogy with, to make some kind of analogy with this multiplicative hypertoric varieties and try to see if we can we can actually implement this Aganagish program in this setting. So that's what I actually want to discuss in the remaining time. So let me just ask this question. So the question will be like, okay, can we extend this picture, extend this picture beyond the hypertoric case? So by the way, so I had to say that Gamache, McBean, and Webster, they said that they don't think that this conjecture holds beyond the hypertoric situation. But my feeling is that we can get some similar type of conjecture beyond the hypercolor, the hypertoric context, and that's what I want to discuss with you. So somehow from now the things will be more speculative, and so you have to take my words with some care, but that's good. That's at least from a point of view, that's also the way we do mathematics, right? So we formulate wild and imprecise conjectures and expectations, and then the the world is trying to to make these wild expectations and conjectures precise and make make them into theorems. That will be that's the work. So let me say the idea. What will be the idea of answer this question? So there are some heat chain systems, and I will explain everything I will say here. So there are some heat chain systems, right? Associated to certain class of physical theories, associated to associated to a class S theories, right? So the efficiencies associated to a class of studies also appear in the four-dimensional n equal to context. Mhm. So what I want to say is that they are kind of analog to multiplicative hyperton barrel. So what I want to say is that for this kind of heating system, a picture similar to the Aganagi's picture and this Gamache-McBreen-Webster conjecture and this Landau-Ginzburg theorem should works, right? And then, okay, so let me just discuss what, in a very uh, short word, what the Fisher system is and what the class theories are and how to put together this thing in kind of mirror symmetry for Fisher systems. So I will just say something about Fisher systems. Very, it's a kind of very brief uh, discussion about this. So what is the origin of this thing? Actually, Hitchin study. So Hitchin study the model space solutions to certain self-duality equations. Right? On a Riemann surface C. That's it. Okay. So let's denote this model space by M heat. So let's denote it. Let's denote this model space M heat. Right? So we have that the G is a complex, well, not integral, it's complex relative. So then we have that this M heat is a hyperkähler actually. It carries a hyperkähler metric, so carries a hyperkähler metric. Hyperkähler manifold metric. Okay, so with complex structures, I, J, and K. That's these are the complex structures, right? So now consider a G bundle E. So let E be a G bundle. And consider this what is called actually the Higgs field. Phi is well belongs to H0 C is at the tensor K. Here K is canonical bundle, the canonical bundle, the canonical bundle of C, sorry, of C, and this is the John bundle. John bundle, right? Okay, so this phi here is the Higgs field. It's called Higgs field. Okay. So now we want to consider the pairs of this bundle, these G bundles with the corresponding Higgs field. So let me just denote by T double will be use the model space of pairs E thing. Fine. Okay. So if we take the complex structure if we take, so taking the complex structure, I in M heat, right? We have the following identification. So we have that the M heat with this complex structure I actually is uh, M double. Okay. So how about if we fix the other complex structures? We fix we fix J and K. So for J and K, okay, we have the following. So we have that we take M heat and we fix the complex structure J. So this is actually isomorphic to the M heat fixing the K complex structure, and this is actually called the RAM model space, right? So this the RAM is just the model space of flat G connections. You see, okay. So we have once you fix this complex structure, so we have two kind of spaces, the ball and the RAM, and then they are actually related, right? But also, which is something which is really important in this theory is the existence of the so-called Hitchin map. So we also have the so-called Hitchin map or Hitchin vibration. The so-called Hitchin map also known as the Hitchin vibration. So H is known for the double with this A, say this Bennett sum E I equal N to N H0 C K I. So what we have is that we take this pair here and we send to the determinant of this. Okay. What Hitchin actually proved, and is important for us, is that Hitchin actually proved that it H actually is an algebraically completely integrable system. So this is will be important for us. That will actually be one important part of our picture. So let me just set this, make this small remark that will be probably helpful in our picture because I won't discuss this today, but probably will be important. Like that we may require some punctures in C. So we can consider not just the Riemann sorted, but some kind of punctures with some punctures with some mark points in. Yeah, that will be we can, and that will be probably the most general picture. And for the ideas I want to discuss today, maybe that will be relevant. But for today's talk, it's not really important, but it could be. Okay. So, the literature about Hessian system is huge. So there's a lot of work in this topic. Actually, I think, Madrid and in particular, Complutense and ICMAT is very, there's a lot of big experts in the theory. So you probably know uh, more things than me about this Hessian system. So probably you're more experts. I mean, I am not really an expert in Hessian theory, right? So the amount of work is quite big. But there are actually two recent developments in the Hessian theory which are somehow relevant for the picture I want to describe. So let me just mention that there is two recent developments in the theory of Hessian systems. How relevant for our proposal or what I want to propose. So these two things are, the first one is so-called enhanced mirror symmetry of Hessian systems. This is a work by Hossel and Hitchin. I think it's a work from 2024 or something like that. And the other thing is some multiplicative version. So multiplicative version of Hessian systems. Okay, in the context of supersymmetric gauge studies. This is the work by Elliot Preston. Okay, so let me just start saying something about enhanced mirror symmetry. So of course, I mean, my account about mirror symmetry of Hessian system is incomplete. I want to discuss this very relevant work by Kapustin and Witten, and the relationship between mirror symmetry of Hitchens and geometric Langlands conjecture, which is also somehow related with what the Elliott and Pestul did, because Elliott and Pestul they wanted to have some kind of multiplicative version for the geometric Langlands. So I want to discuss this interesting work, but there is certainly a task will be try to relate the ideas I'm going to discuss with you in this very general picture coming from the work of Kapustin and Witten. And I also want to discuss the classical work of Husserl teaching, but Husserl actually they discuss somehow mirror symmetry, and they discuss some mirror symmetry for Hitching system as SYZ uh, uh, vibration. So he did some work about that, and somehow using this kind of work, what Husserl and Hitching tried to do was, to extend uh, this picture when you actually consider the action of a torus. So in this enhanced mirror symmetry, what Husserl and Hitching did, so they consider the sister action, okay, on the modeling, the Hitching modeling space given by, so you take this pair here and then go to this lambda space, so you use scalar. So this lambda is a complex number, so it's okay, it's non-zero complex number. So it's scalar multiplication of the history. So that's the relevant part for me was that they wanted to consider the mirror symmetry for Hitching, in the sense of the LYZ conjecture, as Husserl did before, and now they consider an action vector. So they want to consider some kind of equivariant version that was actually relevant, because when we look at this picture by Aganakis, we really need some action of the torus, so we need to work equivalently, right? And in fact, in this work, Husserl and Hitching, they define some core with respect to this action. So with respect to this action, to this system action, so the core, I call C here, and here was defined, or can be defined. So in fact, they defined this as a reduced scheme of the nilpotent cone. That's the definition they use, right? So the core in this case is the reduced scheme of the nilpotent cone. Which is H1 minus 0, right? And of course, and it is Lagrangian submanagement. So, so it's really tempting to compare this core with the core we define in the work of Hagana. In that work of Hagana, you also have a torus, a little bit more complicated, because the sound is made by the product of the part of the torus that actually scales the harmonic symplectic form. Certain torus, with the dimension is the rank of the of the Lie algebra associated to the gauge group, right? But then again, I mean, philosophically, here we have somehow the same thing, the same picture. So we have some torus action, and then we can define some Lagrangian submanifold of the space by using somehow the action of the torus, right? So I will propose like that. What will be somehow the so we can ask, okay, what will be probably the mirror of the score in this setting, or probably we need to modify, the action, get another action, and to get another core. That's not clear. So what is now so now suggesting this picture is okay that there should be some picture mirror symmetry that consider this core, right? So that's the what I found. This is what I find interesting in this Hausel and Hissing work. That they incorporate this action in the mirror symmetry picture, which was not actually considered before in this setting. Right? Okay, so the important thing is okay. So Hitchin and Hausel also include this action in the mirror picture. And then this is what is called enhanced nuclear symmetry. So for the Hitchin system, right? So consider it, I mean, essentially for me, that's the idea of it. The picture is more complicated, right? I mean, it's more things in the paper, but essentially, you want to extract the main idea of this work. For me, is okay. We now incorporate this torus action, and then we see how this action actually interacts in terms of mirror symmetry. Good. That's the enhanced picture. The second development what I mentioned was the multiplicative heat chain systems. Well, let me say something about that system. Right? Good. So let me define a multiplicative Higgs bundle. So a multiplicative Higgs bundle on a Riemann surface C is a G bundle. Just let me change the notation P before I call it E, but because it was the usual. So now I want to use multiplicative. So let me change my P. So it's a G bundle P on C, okay, with a meromorphic automorphism G. So what does it mean? So this means, what is the difference between this and the usual Higgs bundle? So this means that in the usual definition, usual definition, so we change, you have to replace, you have to replace the adjoint bundle, to replace the adjoint bundle, the adjoint bundle with denoted P by the group value So with the values in the Lie group, with the group value at join bundle. Okay. So that's the difference, right? So again, if you consider the modular space of these multiplicative Higgs bundles, so the modular space of these objects admits a version of the Hitching map. And you can ask, okay, so you have a version of the Hitching map, that's good. So you can ask, okay, we have integrable system like in the usual situation. So let's discuss this. Okay, so let me make a couple of remarks. So let me make 3 remarks. The first one. Okay, so I want to address this question. So in this Hitching map, in this context, in this multiplicative concept, defines interval system. So the answer is not in general. So the multiplicative map so makes sense for any chord. Okay. However, however, only defines a completely integrable system in the Calabi-Yau case. In the case C, when in the case where C is Calabi-Yau. How in the cases when C is complex numbers, torus, or an elliptic chord. Right. Anyway, considering right this thing. In this case, somehow in this case, in this Calabi-Yau case, in the Calabi-Yau case, the resultant modeling is hyperkähler. Is hyperkähler. Okay, so we have in a good way. So this kind of this multiplicative. So we get some kind of multiplicative uh, variety, right? I mean, in certain sense, we can think of the usual the usual Hitching system as a multiplicative manifold, but also sorry, a multiplicative variety. But also here there is this particular, set of examples, which is actually called also multiplicative Hitching system, which also could play the role of this multiplicative repertory variety in sense in at least in some particular cases. Also, it will be also interesting to see in this picture if we actually need. I mean, of course, the point is that we need the more space to be hypercolor. So probably the general situation is not really fit into the picture I want to describe. But maybe it will be kind of interesting to see for general multiplicative Hitching system what will be the mirror picture, right? The 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 second remark, the third remark, which is important for us, is that it's from the physics point of view, which was the starting point by Elliot and Preston. So Elliot and Preston, they are Actually, we started with the physics discussion. So they said, okay, there are two sources for multiplicative Hitchens systems. So from physics, from, from the physics point of view, from the physics point of view, okay, that exists two sources, two main sources for multiplicative Hitchens systems. Right? One of the source is model spaces of solutions to equations of motion in certain bidimensional supersymmetric gauge theory. Gauge theories. So this is very interesting. That probably related with this is related what this multiplicative Lagrange geometric Lagrange program, but I don't want to to consider this thing, but it's good to know that there is this sort of example. And the second one is more interesting for me and for the proposal I want to construct, which is the other source of example is the Saber-Witten integrable system of 4D n equal to 30. Right? Did you look at this B and we go back to the beginning of the discussion today? Is the beginning of the discussion today, right? Okay. So here, so we say that some source of this multiplicative hypertrophy variables can be seen as as kind of Saber-Witten system related with this for the n equal to 30. So this actually suggests a very very close relationship between this thing and this multiplicative Hessian system of fluids, right? Because they are also coming from this kind of theories. So this really suggests that okay, maybe we can use these multiplicative Hessian systems in order to understand the agamamish picture beyond these hypertonic cases, right? That would be really, this is really suggestive, right? But we can ask, okay, that is probably used for this multiplicative, of course, and the name, multiplicative is already, you know, very appealing. But we can ask, okay, that probably it's just this multiplicative Hitchens system, or maybe we can consider in a certain sense certain Hitchens systems as kind of multiplicative, analogs of kind of analog of multiplicative hypertonic varieties. And that's probably true. And we should actually just look at how actually these Hitchens systems came from the class studies. So let me just discuss what is class S theories means. Yeah. This is, to see if not just multiplicative, but usual Hitchens system can enter into the picture. So So let me just start with this motto by Andy Naisky. So Naisky, this motto. So let me just run it. So the relation between n equal to Paris and Hitchin systems is that the Hitchin system arises as the model space of the n equal to 30 compactified on a circle, right? And this is very interesting because, if you remember what we did last time, so when we constructed the mirror for the column branch X, remember that the column branch was related with a three-dimensional 30, not with a four-dimensional 30. But when we take the Y, that was the column branch of some 4D 30, like what is here, for the multiplicative version or something like that, right? But then we compactify on a circle, and then by this compactification, we reduce the dimension, and we get a three-dimensional 30. So that's what I want to describe now. And that's what actually this motto by Andy Niske is saying. So you consider some kind of n equal to 30, and then you compactify on a circle, like that you get somehow that Hitching system. And in certain sense associated to the three-dimensional 30, that's also somehow this Hitching system that should be is kind of close to the column branch. So, right, some kind of related with the kind of the additive uh, hypertonic variety, right? So in a certain sense, so the Hitching system would be more like kind of additive, uh, right? Additive variety. So, right, I mean, somehow how this relation between additive and multiplicative via mirror symmetry is still a little bit, confused for me, but you know, that's somehow the core of of the picture of the proposal I want to make. So how actually use this duality between somehow the mirror symmetry in this context, there should be this duality between additive and multiplicative varieties. That will be somehow the idea. Okay. So let me just mention so what what kind of good what are actually the n equal to 30s we need to consider. So the n equal to 30s is mostly related to Hitching system, to Hitching systems, right? Are the so-called class S things. And then I will say what is this? Okay. So what is a class S in a nutshell? So very rough definition. So this is a three-dimensional theory three-dimensional theory. Then from a six-dimensional one, and so let me say this is why DS. So DS means because come from a six-dimensional theory. That's the S in the name. So because it comes from a six-dimensional from a compactification. So how do you get? So you start with a six-dimensional theory. So you have to reduce the dimension. So you reduce the dimension by using some compactification. So from a compactification, on sigma times S1. So sigma is a Riemann surface, right? So you see, so what it says that you have a six-dimensional theory, so you compactify using you compactify on sigma, so this reduce the six-dimensional to a four-dimensional theory, and then a further compactification on S1 produce a three-dimensional theory, and that's the S theory, right? So let me just write this thing. So compactifying on the Riemann surface produce a four-dimensional theory and a further compactification and a further compactification on this one produces a three-dimensional. So so there are some theories. So and doing the compactification with this. So how the actually questions of how the heat system appear in this picture. So how heat system, how the heat system, how heat systems appear. Okay, let's see. So let's start with this. Uh, so when we have this first compactification in the Riemann surface, so we get a four-dimensional theory. So let me start with this four-dimensional theory. So let's consider. So you start with a six-dimensional, so you get a four-dimensional compactified on sigma. So let's consider this four-dimensional thing. So let's consider the four-dimensional n equal to supersymmetric theory denoted not by T. Okay. So then could be its column branch, the is column branch. So this is the column branch of the four-dimensional theory, and what we see is that the B consists of an open regular locus B and a discriminant locus the singular locus. So we would just need to consider the regular locus. So we don't need to consider the singular locus, but all the discussion actually can be extended to all B, right? And not really sure if all B will be really needed, but I think it's enough to consider the regular locus. Okay, so the important actually observation is that there is no single Lagrangian, a single Lagrangian um, describes the theory globally. There is no single Lagrangian describing globally the theory, but uh, there is a single geometric object. There is a single geometric object in which we can describe, I mean, all the Lagrangians locally. So all local Lagrangians can be described. And the interesting thing is that this object, this geometric object, is an integrable system. So that object is a complex integrable system. Integrable system associated with G. So what is the moral of this thing? So you start with a four-dimensional n equal to supersymmetric theory. So there is a way to associate to the theory a complex integrable system. That's the thing. So and what we want to see is this complex integrable system is actually a Hitching system. That's what we want to show. So okay. So let's discuss it more concretely, these pictures more concretely. More concretely. Okay. It says holomorphic, holomorphic, symplectic manifold, magnetic, let me call it I prime with a projection, So let me call it pi and I prime to be red, such that this current U is the factor, right? Pi minus U are compact compact complex Lagrangian core. You have these vibrations, all right? So that this is will be, the Hitching vibration, right? Okay. So that's for the four-dimensional theory, right? But we want a three-dimensional theory, so we need to compactify. So this is jet is not a Hitching system, right? This is just a complex. This is just a integrable system, completely integrable system. But we want to make it a Hitching system. So we start with a four-dimensional theory. So we need to compactify on a circle in order to get the three-dimensional theory. And when we compactify on a circle and get the three-dimensional theory is when the Hitching system actually arises. So let me just write this thing. So the three-dimensional theory the three-dimensional theory, will obtain a complexify on S1, right? It's a sigma model whose target M is related to the complex integrable system I. Okay. How is this relation actually? How does this relation work? Let's see. So the crucial part is that there's some constraints. So the constraints of the n equal for supersymmetric theory in dimension 3. So what we are getting is a three-dimensional n equal 4 supersymmetric theory. Okay, force that the metric from M must be hypercolor. So in this three-dimensional thing, we get a hypercolor manifold. This means actually that this M carries a family. There is a family of complex structures G shape, right? And this psi is in CP1. Okay. But there is one which is actually distinguished. So one of the complex structures is distinguished, right? So let's denote it by G0. And when we consider actually the holomorphic symplectic manifold in this distinguished structure, so we identify N with the I prime. So, and when we consider, when considering, right, it's a holomorphic symplectic manifold, holomorphic symplectic manifold. In this particular complex structure, so M, the target space M is identified to the I prime. So this I prime comes from the four-dimensional theory, but then when you consider this compactification, we get a target space M. You have this family of complex structures of M, but there is a one complex structure that actually make as a holomorphic symplectic manifolds. We actually identify this M with this I1 and then I prime, and then we have a Hessian system. So for the class study, we have this compactification. So for class studies, the complex integrable system. Okay, if the complex integrable system is a Hessian system, so okay, if the four-dimensional theory came from this reduction of a six-dimensional theory, a class study, so the complex integrable system we get is a Hessian system. So for class studies, the complex integrable system is a Hitchin system. Because this identification, this reduction is for any four-dimensional theory. So we get an integrable system, right? But we don't know if it's a Hitchin system or not. But if the four-dimensional theory we have came from a six-dimensional theory, so by the compactification on a Riemann surface. So this means that the fault theory is the three-dimensional theory we get is a class S theory. So in that case, the integrable system we get is actually a Hitchin system, right? And somehow this Hitchin system looks like the X in the in the in the Garagos picture, and actually for this additive hypertonic in the case of Gamache, McBreen, and Webster conjecture. So let me just write proposal two. So proposal two, the second thing I want to propose for you. So the second thing is there exists a complex structure its shape such that, so in this family, as a complex manifold, this M should be the I prime minus some divisor for some divisor D of M. So that we should somehow we can get somehow the mirror. You say that you have the mirror of the thing for J0. That's what I want to say in this proposal. So that in the family you should find somehow the mirror of the J0, right? And then that's the proposal, the third proposal, right? Is okay, the mirror of, let me call it let me call it additive variety M. Of course, I am using additive for multiplicative and in a very, not precise way, but I think you can understand what I mean. So the mirror is a Landau-Ginzburg model, W from this A prime to see this I prime because it's the one we get in the proposal two. So what I am trying to do is so the proposal two is kind of the analog of Gamache, Gamache McBreen and Webster conjecture, and the proposal three so should be the analog of the theorem of Lau and Chan. That's what I want to propose. So, but then I want to also incorporate the torus axis. I want to enhance the picture. So consider if we consider a torus action on M, certain torus action, right? Some extra terms in the notation of the language we used in the previous lecture. So twisted masses, I think that will be twisted masses, should be added. So in this, what I'm saying that in this contents of this mirror symmetry for this Hitchin system associated to class S theories. So the mirror of this thing that should be Landau-Ginzburg model, but I mean, if you consider the equivariant action of the torus action, so you want to consider the equivariant mirror if you want. So what you get is a Landau-Ginzburg with twisted masses. That's what this proposal is saying, right? So should be that, right? And then they should reflect somehow the equivariant parameters of the action. And then so how you have the somehow you have the upstairs. But what actually the enhanced mirror symmetry by Hitchin or Husserl, sorry, Husserl and Hitchin suggests, and also Ganaji suggests is that when you have this torus action, so you have this natural idea of curve, and then if you have this curve, maybe you can try to make this downstairs mirror. So this is really speculative more than the other proposal. So proposal 4 is like we have the following diagram. We have the following diagram. This is really an optimistic diagram, right? I mean, I guess probably the diagram in the form I am writing it is not really correct. I think it's too optimistic, but I think that we can somehow elaborate on this picture. So what we have, so we have this Hitchin M, right? This hypercurrent manifold M, and you have some torus action here. But the other, what we said before, like this I prime with some W here, there should be the mirror, there should be the upstairs mirror, right? This is what somehow we discuss uh, so far, right? So this I is like the multiplicative version, right? It's kind of the multiplicative version of this additive M variety. But then if you have this torus action, there's something that can be this define this curve, right? See, like like what Hauser and Hitchin did. And then there should be here a mirror of downstairs mirror of this curve. This is not the complex number, right? This is let's change this because it seems like no, it's not the complex number. This is on curve, this thing. Okay. Downstairs mirror. So what will be my proposal? So the mirror will be, of course, the Hitchin vibration here. This should be here, irregular with some W here, right? Not the following thing. Somehow this BREC is actually the column branch of the four-dimensional theory, essentially. And when we actually did the Aganagish picture, the column branch was not in the down part, but the upstairs part. That's something that is kind of confusing for me. So that's why I think that it's probably this picture I am drawing here should be actually improved because I don't really sure if what we have to put here is this vibration, the hitching vibration. So, but it seems that this the natural thing to consider, right? But of course, I mean, you also had I'm also claiming that the space here, the mirror is actually the mirror somehow. I mean, we can have up the Landau-Ginzburg model, which is the mirror of the car. What will be the car? I mean, in order to get the mirror here, right? I mean, it's not really it's not that clear, but philosophically speaking, that's what we should get. And then, of course, there should be some diagonal here, the equivariant mirror in diagonal sense, right? That should be the equivariant mirror. Okay, of course, there should be some relation between this W and this other W. So some coordinates, you take the derivative of this thing equal to 0, they give you, this is the Y, give you Y. Yeah. Right? That will be, and that's this picture actually is the this diagram is the diagram and I actually draw before last lecture for the Aganagi picture when we have the column branches and everything, right? But somehow the analogy somehow that this M is like replacing this additive variety, which is actually some kind of variety associated to some three-dimensional theory. This I prime will be like the analog of the multiplicative variety, right? That we can also expect that we can also incorporate here a torus action. So the curve will be defined, this vibration will be right, and we also have the new non-stairs. So finally, I want to write the the last proposal. The last proposal will use okay that we so what we need for the Ganagish theorem. So remember that for these color branches, this kind of hypertonic varieties. So there is a well-defined Gromov-Witten theory, equivalent Gromov-Witten theory by the work of Kunkov and his collaborators, right? Some kind of with quantum cosmology for Nakajima queer variety. This is none, right? And but I don't know. I mean, I don't know any equivariant Gromov-Witten theory for Hitchins systems. So I don't know what this theory looks like. But I didn't say that. But most of the motivation of this project related to Hitchins system was to see how far or how close are Hitchens system and Nakajima queer varieties. That was actually my original, and it's kind of my big goal. I mean, to just to compare and to see how what are the relationships between Nakajima queer varieties and Hitchens system. So my last proposal is that we can consider a genus zero Gromov-Witten theory for Hitchens system of class S. The Hitchens system related with this class as 30s. In this along the same way, along the same ideas, we construct the Gromov-Witten theory for the Nakajima weir varieties. So the final proposal is the equivariant genus zero Gromov-Witten theory for Hitching systems. Yes. Of classes mean that came from this physical theories can be constructed. So for this kind of hyperkähler manifold UI can be constructed all on the same line, the same lines. Then the one for Nakajima queer varieties, for Nakajima queer varieties. Okay. If we can do that, my expectation is that in this case, we can produce or we get a semi-simple Frobenius manifold. So essentially what I mean is like we get some simple quantum cohomology and then applying given tal telemann reconstruction, we get the all genera information, right? And doing that, somehow the what we should get as a corollary of this thing that we get in one formula, we get an analog. Okay, we have a Hitchin analog for the Hitchin system analog of an Aganavish. Sorry, for the equivariant mirror symmetry. Okay, so that's the thing. So what what I want to say in short, I wanted to say in few words is the following. So the mirror symmetry for the Hessian system. So we can try to uh, describe an equivariant mirror symmetry for Hitchin systems in the sense of Paganavich. In that sense, actually, we need to use this kind of physics heuristics, and the mirror will be this Landau-Ginzburg model with twisted masses. And somehow, very general philosophically speaking, so you have this duality between additive and multiplicative varieties in certain, sense. So the mirror symmetry is related with some, you need to construct some Landau-Ginzburg model, which should be the mirror of these additive varieties, and the space of this Landau-Ginzburg model will be the multiplicative variety. And then you can incorporate a torus action and get a picture of the equivariant mirror symmetry, right? So this is, a dream. This is somehow some program, and I think this is the kind of things I am doing these days. And so it was very, nice for me, and I'm very glad that I could share this set of ideas with you. And maybe if you find something interesting, it will be perfect. So thanks, Marina, and thanks everybody for being here and listen to me. Thank you.
Thank you, Alex. That's great. Um, okay.